Hi, my name is Tan Ju Yang from Section 2, Group 6. In this video, I will be the group representative to demonstrate the whole process and also our result obtained of this group project 1. My group members are Brian So, Lin Wai Jing, and also Daniel Lin. First of all, I will show some overview flow of this project. Firstly, we are given the input image in .png file, and we have to convert it in the grayscale conversion, and eventually we will obtain the input image in .dat file. By taking this input image in .dat file, we have to apply the sharpening filter in both Python and also in C. So throughout this C process, we have to go through the C to RTL synthesis, C to RTL coordination through the Vivado application in order to figure out the performance between Python, C, and also the FPGA usage in terms of slack, performance, time execution, time consuming, and so on. And this is our Python code for define the sharpening filter. First, we have to read the input image in .dat file in order to read the actual pixel value of it. And this is how we define the dimension of the input image and also our sharpening filter kernel. And this is the function to perform the 2D array convolution, which is how we perform our sharpening. So our width and height of the image is 512 times 512 for the dimension. And this is the kernel for the sharpening filter, which is in 3 times 3. And this is our C code for the sharpening filter. Our image size is 512 times 512, while our sharpening kernel size is 3 times 3. And this is the filter function to perform the convolution, initially in 2D array. And this function is very important to prevent the overflow and underflow condition. And lastly, we have to do the flatten process in converting the 2D array to 1D array as our output image. And this is our C testbed for our sharpening filter, and this is our kernel used for the sharpening, and this is our our first function to read the pixel value for the file, and this is our testbed to perform the convolution, which is the sharpening process. And we save our output image in the 1D array result. And this is the final function to perform the to check our consistency after we compile and run the output. So this is our desired output for performing the whole process of sharpening. So let me go through the report result file. And these are the three input image chosen for performing the grayscale conversion as well as the sharpening process. And this is the performance comparison for these three image, and this is obviously show that by using the C as the platform, the time consuming or time execution is the shortest, while by using the Python as the platform, the time execution is the longest. And this is the initial condition to set up the Vivado HLS for the C to RTL synthesis. The clock period we taken as 10 nanosecond, and the uncertainty is 0 nanosecond. And this is the synthesis report. This is the parameter usage for the FPGA, 0 VRAM usage, 6 DSP usage, 605 flip flop, and also the 855 block. And this is our latency performance, and this is our estimate clock period obtained, which is 9.4 nanosecond. And from this C to RTL code simulation report, we obtain the latency, which is 1300507, and this latency will be proved later. And this is the C to RTL code simulation waveform in overall site in overall view. And in this process, we have to figure out the clock period required for the AP start and also the AP dot. And the clock period for AP start when it is equal to logic 1 is 136 nanosecond, and this is the clock period for the AP start. And by using these two clock period from AP start to AP done, we will get our desired or required clock cycle, which is 1300507, which is tally with our coordination report, the latency. And this is the synthesis and implementation report, and this is the tabulation for calculate the FPGA performance. Throughout this Vivado, we can looking at the timing constraint performance. The slack we obtain is 3.967 nanosecond, and this is the FPGA resource usage parameter in the Vivado, and this is the power consumption in the FPGA usage. There is a 9% out of 100% is the dynamic power, and the 91% of the total is the static power. And this is the report that we obtain after we implement our FPGA usage. So our conclusion of this project is that it obviously showed that the sharpening performance in C++ is much better than in Python as a platform. So the all objective of this project have been achieved successfully. That's all from session 2 group 6. Thank you.